Magic Squares of Squares. Part 1. Minimal Representatives. A proper 3x3 magic square of squares is a 3x3 matrix containing 9 different integer square numbers, where each row, each column and each diagonal sum up to the same number m. We call that number the magic constant. In any proper magic square, the number in the middle is a third of the magic constant. This can be shown via a linear equation system with the 9 numbers and the magic constant as variables and the 8 magic sums as equations. Since the sum of all 9 numbers is 3 times m, in a proper magic square of squares, the sum of all 9 squares is a square again. Currently, it's not known whether a proper magic square of squares even exists. But if we found one, we would immediately get infinitely many from it. The most trivial thing we can do to derive new ones from the first is to rotate or reflect. So we get 8 different versions with the same numbers. The second most trivial thing we can do is to multiply each of those 8 versions with any square number. The result again contains 9 different square numbers, and the sums of rows, columns and diagonals all increase by the same value. This is boring. So let's consider all proper magic squares of squares that can be derived from each other in one of these ways as equivalent. This means, when looking for the first ever proper magic square of squares known to mankind, it makes sense to look for a minimal representative of such an equivalence class. In other words, a proper magic square of squares that cannot be divided by a square number. In this sequence of short videos, we'll have a look at the prime factors in a minimal magic square of squares. Check that out. I mean, seriously, check that out.